Sample problem 8.4, determine if each of the following is a spontaneous process, a non-spontaneous process, or an equilibrium process at the specified temperature. So we're given several different reactions, and we're asked to determine whether it's spontaneous or non-spontaneous. So here's the logic. What you do is you calculate the total change in entropy, which we'll call delta S of the universe. Okay, that's the total entropy change. And that is equal to the change in entropy of the system. And for that calculation, what we'll do is we'll use the standard entropy values that are in Appendix 2. So for this one, use the standard entropies at 298 Kelvin. Okay, those are in Appendix 2. Plus, now for this one, what we're going to do is we're going to have delta S of the surroundings. But there are no values in tables for entropy values in surroundings. So what we do is we use this relationship. Minus delta H of the system divided by T. Okay? That equation will give us delta S of the surroundings. And then we use the following logic. If delta S of the universe is greater than 0, positive, then it's a spontaneous process. If delta S of the universe is less than 0, it's negative, then it's a non-spontaneous process. Okay, so our calculations are involved here. These are not simple calculations. The arithmetic is very easy, but it's involved in terms of looking up data. This is something we often do in thermodynamics, is we look lots of data values that have been measured up, and we have to find the data values and then use them in our calculations. So we need to look these values up, we need to look these values up, and then what you'll see is that for each of these problems, the temperature is given. And just to make it a little more involved, the author of this problem has decided to make the temperature different for each of these calculations. Okay? So that's the idea behind it. So let me, actually we'll just come down here. Let's take the first equation. Okay. The first one is H2 plus I2 to become 2HI. H2 gas plus I2 gas to become 2HI gas. And then again, they tell us the temperature, 0 degrees C. But keep in mind, whenever we do thermodynamic calculations, we have to convert that to Kelvin. So we're going to make that 273 Kelvin. Now, in fact, it's 273.15, but I'm going to go ahead and just use 273. We don't need to be quite that involved in terms of the sig figs here. So we have to look these values up. So what I'm going to do is I'm going to look up the standard entropy values, and then I'm going to look up the delta H values for each of these. Okay? So for the first one, the standard entropy value at 298 Kelvin, although we're going to use these values even though the temperature is not 298, is 131.0. Okay. The delta H of formation of hydrogen, we look that up, it's 0. That's nice. Then we do the same thing for I2. The standard entropy of formation is 260.57. And again, it depends on the state of matter, so we have to really be careful when we look these values up. The delta H of formation is 0. Okay. All right. Now we move on to the HI. For the HI, the delta S, I'm sorry, the S, the standard entropy for HI is 206.3. And then delta H of formation for HI is 25.9. Now, we have to be careful. This is in joules per k-mole. Entropy values, standard entropy values are joules per k-mole. Standard heat of formation data are in kilojoules per mole, not joules, but kilojoules. So that plays a role in our calculation. So here's what I'm going to do. Delta S of the universe is equal to delta S of the system plus delta S of the surroundings. Okay? So let's do delta S of the system first. We learned how to do that in the previous sample problem. It's the sum of the entropy values of the products minus the sum of the entropy values of the reactants. Okay? So for this reaction, we do products minus reactants. So 2 times 206.3, that would be the products. We would subtract from that the reactants. So 1 times 131.0, well, let's put these in brackets, plus 1 times 260.57. Okay? And that will give us the delta S of the system. Okay? Not the universe, but just the system. So this is only one step in this calculation. So 2 times 206.3. 2 times 206.3 is 412.6. We're going to subtract from that 1 times 131 plus 1 times 260.57. 1 times 131 plus 1 times 260.57. Close the parentheses, and you get 21.03. Joules per k-mole. Okay? So there's delta S of the system. But now we're going to do delta H of the system. Now delta H of the system is delta H of the reaction, which is the sum of the number of moles of the products times the heat of formation of the products under standard conditions minus the sum of the number of moles of each reactant times the standard heat of formation of each reactant under standard conditions. This is something that's covered in the previous course of general chemistry. So that would be delta H of the system. That would be these values here. Now luckily, the reactants are both elements. In their standard states, they're both zeros. Okay? So actually, let me check. Just check real quick. I'm sorry, I have a mistake here. It's not 0 for I2, it's 62.25. I just went back and checked it, and that was incorrect. It's not 0. There we go. Okay. So let's come back over and try this then. So let's do products minus reactants. So it's 2 moles times 25.9. So let's put those in brackets. So that's the products minus the reactants. The reactant side would be 1 times 0 for hydrogen, plus 1 times 62.25 for the iodine. Okay, so let's see. This is 50. Let's make it a little bit easier instead of punching all the numbers in the calculator. This would be 51.8 minus 1 times 62.25, so that would be 62.25. Okay, so 51.8 minus 62.25. So that's negative 10.45. Okay, now the issue here is this is kilojoules per mole. Okay, so this is going to come up as an issue when we do our final calculations. This is delta H of the system under standard conditions. When we do this calculation of delta S of the surroundings here, it's minus delta H of the system divided by T. So that means we have to change the sign and then divide that by the temperature. So delta S of the surroundings would be minus a minus 10 point, I'll write it out here, minus a minus 10.45 over T. Okay? So this would be 10.45, 10.45 kilojoules per mole divided by T. Since this is at 273, we'll put that in there. Okay? Now, here's what happens. When you take 10.45 and you divide 10.45 and you divide that by 273, you get 0.0383. 0.0383. Kilojoules per k-mole, right? That's delta S of the surroundings. Now here's the issue. The issue here is that this is in kilojoules. If we're going to add these two values up here together, they have to have the same units. This is a different unit. It's joules per k-mole. So we need to have them in the same. So what I'm going to do is I'm going to multiply this by 1,000 joules per kilojoule. That will eliminate the kilojoules, and we'll get 38.3 joules per k-mole. Okay? And that's essentially how it's done. Now, we can add those two values together. System plus surroundings. The system change was 21.03 joules per k-mole. The surroundings is 38.3 joules per k-mole. If you add those together, you get 59.33 or 59.3 joules per k-mole. Okay, so 59.3 joules per k-mole. And there you go. Okay. All right, so that's the idea. So you find delta S of the universe by looking up the standard entropy values in Appendix 2 to find delta S of the system. You look up the delta S of this, you calculate the delta S of the surroundings by looking up delta H of the system, and then taking the negative of that and dividing it by T, adding those two values together, and now you've got your answer. Okay, let's try one more. I'm going to try part B. Part B, let's do it right here. Part B is CaCO3 solid goes to CaO solid plus CO2 gas. Okay, that's essentially the idea there. So we're going to look up the standard entropy values for each of these materials. So for these values, it's a lot of numbers here, right? You can see that's a lot of numbers here. So let's look it up for CaO. So I'm sorry, for CaCO3. CaCO3 is 92.9. CaO is 39.8. And then CO2 is 213.6. Okay, so let's from that get delta S of the system. Products minus reactants. So 1 times 39.8 plus 1 times 213.6. Put that in brackets so that we know that's the products, minus 1 times 92.9. Put that in brackets. Okay? So 39.8 plus 213.6. So 39.8 plus 213.6 minus 92.9. 160.5. Fair enough. Again, that's joules per kmol. Okay. Now we're going to do delta S of the surroundings by looking up the delta H of formation values for each of these. Okay. So when we look up the delta H, let's see if we can find these values for CaCO3. It's negative 1206.9. For CaO, it's negative 635.6. And then for CO2, it's negative 393.5. Okay. So now delta H of the reaction, or we'll call it delta H of the system, would be products minus reactants. So CaO, put in brackets, 1 times negative 635.6 plus 1 times negative 393.5 products minus 1 times negative 1206.9. Okay, there you go. So 635.6 negative plus 393.5 negative equals. Now we're going to subtract 1 times 1206.9, and you get 177.8. Kilojoules per mole. Notice it's positive. So delta S of the surroundings is equal to minus positive 177.8 kilojoules per mole. But now we have to divide that by T. So for this particular one, it's 200 degrees C. So that would be 473 Kelvin. Okay? So negative 177.8 over 473. So make that negative. Divide that by 473. Negative 0.376. Okay, now that's kilojoules per kmol. So what do we got to do? We got to convert that to joules. So 1,000 joules per kilojoule. And what we end up with there then is minus 376 joules per kmol. That's a pretty big negative value, right? A big decrease, okay? Is that right? Yeah, that's right. That makes sense. And the reason for that is we have to put a lot of energy. It takes a lot of heat to make calcium carbonate decompose. Decomposition reactions often require energy, quite a bit of energy. So that's what's happening here. So now delta S of the universe is the sum. So let's do the system. The system was 160.5 plus a negative 376. Okay, so what would that be? That would be negative 215.5. Let's check it. 160.5 minus 376. Negative 215.5. And that would be joules per kmol. Okay. That means that there's a big decrease in entropy of the universe. So we would call this non-spontaneous. meaning it will not happen unless you put energy into it. That's the meaning of this calculation. So in the first reaction we did, because we got a positive change in delta S, 59.3, that means it's spontaneous. It will happen without us putting in a large amount of energy. But for this one, we would have to put in a large amount of energy to make this reaction occur.